In this video, we are going to talk about software testing. Let's talk about software testing and why it's more than just clicking around to see if something breaks. At this core, testing is the process of running your program with sample data that mimics what real users might do. You're observing whether the program behaves the way you expected. If it does, great. The test passes, and if not, something's off and the test fails. But here is the important part. If your code works correctly for a specific set of inputs, and those inputs represent a larger group, you can start to build confidence that your program will behave correctly for other similar inputs too. So, no, testing doesn't prove your program is perfect, but it does give you a reliable safety net that helps you catch problems early and reason about correctness in a smarter way. So, what does it really mean when your test fails? Simple, your program isn't doing what it's supposed to do. And that usually means there is a bug lurking somewhere. But not all bugs are created equal. In fact, most bugs come from one of two things. The first one is pretty straightforward programming mistakes. Maybe you forget to handle an edge case, or maybe you have got something like an off by one error. Those are super common. You think your loop is processing all the items, but it accidentally skips the last one. The second cause is a bit trickier. It's when you misunderstand what the program is supposed to do. Let's say your program reads from a file, but you didn't know that sometimes the data might be malformed. If you didn't write your code to handle that, it's going to crash or behave unpredictable. That's why testing is so important. It helps you find both coding flaws and misinterpretations of the requirements. And once you find those gaps, you're one step closer to building a program that really works as intended. Let's walk through four major types of system testing, each with a different focus. First, they are functional testing. This is your bread and butter. You're checking if the system does what it's supposed to do. Are the features working? Are there bugs in the logic? You're trying to prove that the system is actually ready for use. Then there is user testing, sometimes called usability testing. This isn't just about whether the features work, it's about whether people can actually figure out how to use them. Are users confused? Can they find what they need? Does the software help them achieve their goals? Next, we have got performance and load testing. This is where you stress the system. You are looking at response time, how fast it processes requests, and how it performs when hundreds or even thousands of users are active. It's all about proving that the app holds up under pressure. And finally, security testing, super important. You want to make sure your system can protect user data and defend itself against attacks. That means looking for vulnerabilities like broken authentication, unencrypted data, or anything else that could expose users to risk. All four of these types of testing give you a different piece of the puzzle. And together, they help you build a system that's not just functional, but also reliable, usable, scalable, and secure. Let's talk about functional testing and why it's such a critical part of building reliable software. The goal here is pretty simple. You want to make sure that your software actually does what it's supposed to do under as many different conditions as possible. That means writing a lot of tests, sometimes thousands, especially if you are building something like a business web application. Ideally, functional testing will exercise every line of code at least once. That's not always easy, but the more coverage you have, the more confident you can be that your system works. But it's not all done at once. Functional testing is staged. You start with unit tests, checking individual functions or modules. Then you move to integration testing, where you combine modules and make sure they play nicely together. Finally, you do system testing, running the app as a whole, just like a real user would, to make sure everything works for end to end. This process continues and scales until you're confident enough to say, yep, we are ready for release. It's a lot of work, but if done well, it means fewer bugs, happier users, and much more smoother launch. This diagram shows how functional testing works in practice, because it's not just about running a few test cases and moving on. It usually starts with unit testing. This is where you test small chunks of your code, like a single function or module, to make sure they behave as expected. Think of it like checking the ingredients before you bake the cake. Once the individual pieces look good, you move on to feature testing. Now you're seeing how those units work together to deliver a complete feature, like logging in or uploading a file. You are testing more interactions here. Next comes system testing. At this point, everything is integrated and running as a full application. You're testing it like a real user would across different workflows and use cases. And finally, you do release testing. This is where you ask, is this thing really ready to go out into the world? You're checking stability, final bugs, edge cases, basically giving the app its last round of polish before shipping. This cycle helps catch bugs early, keep things running smoothly, and gives you peace of mind that your software's solid before it hits production. Let's talk about this testing pyramid and why it's shaped like, well, a pyramid. At the base, we have got unit tests. These are quick, focused checks that developers write to test small pieces of code, like a single function or class. They are super fast to run and usually easy to automate, which means they are cheap and reliable. Move up a level and you hit feature tests. Now you're testing how multiple units work together as a feature, say the login flow or a shopping cart. These take a bit more effort and are typically slower, but they help catch bugs that only shows up when components start interacting. Then we get to system test. This is where you're testing the whole application as a big working unit. You're checking that all the features behave well together. This is the layer where things like performance and security get tested too. These tests are harder to automate, and fixing bugs here can be more expensive. Finally, we have release testing. We have packaged the software. It's basically ready for the real world, whether it's going to the cloud or being downloaded on a phone. You're verifying that what you ship is actually what works for your users. The shape of pyramid reminds us of best practice. Do more testing at the lower levels because it's faster and cheaper, and gradually build confidence as you move up. Let's break down how unit testing actually works while we are writing code. So here is the idea. Every time you write a function or method, something with a clear responsibility, you should also be thinking, how will I test this? You don't want to test every single possible input. That's not practical. Instead, we use something called equivalence partitions. These are groups of inputs that the code treats the same way. If they behaves correctly for one value in the group, chances are it will be behave the same for all of them. But you don't just want to test the happy path where everything goes right. You also need to test where things go wrong. So you include invalid inputs too. things like empty strings, out of range numbers, or unexpected formats. And here is the key principle. If your code behaves the way you expect for these representative examples, you can be reasonably confident if it will behave correctly for others like them. That's how unit testing helps you catch bugs early and build more reliable software. All right, when we are writing test cases, there are a few must-do strategies that help you really stress test your system. First, edge cases. Anytime your input has a range, like numbers from 1 to 100 or a string length, you don't just want to test something in the middle. You want to hit the boundaries. What happens at 1 and 100? What about just outside the range, like 0 or 101? That's where bugs often hide. Next, force errors. Think about all the different error messages your system is supposed to throw. Then try to trigger each one deliberately. You want to make sure your error handling actually works, not just your happy pass. If your program uses input buffers, try to overflow them. Feed it a longer string or huge file and see how it reacts. This is especially important for security testing. Buffer overflows can be exploited if not handled properly. And lastly, if your app is doing any kind of math, you want to check for overflow and underflow. That means testing it with numbers that are super large or super small numbers that might break your calculation logic or even crash the system. Basically, don't just test what you think the user will do, test what the system might break on. One thing that's easy to overlook when designing test cases in how your program handles the weird but possible inputs, and that includes null or zero. If your code uses strings or pointers, always make sure you test with null values, empty strings too. For numbers, don't forget to throw it as zero. It's such a common edge case, especially in divisions or loops. Now, when your program transfers lists or sequence, make a habit of counting elements. For example, if you start with 5 items and filter out 2, your result should be 3. It sounds simple, but keeping track of these counts can help you catch bugs where elements get accidentally dropped or duplicated. And here is a small but powerful tip. Test with a single element in your sequence. You don't be surprised how many bugs show up and only when there is just one thing in the list. One is not like the others, literally. So remember, check your edge cases and don't forget the quiet values like null, zero, and one element list. They will tell you a lot about reliability of your code. When it comes to feature testing, the goal is pretty simple. You want to make sure that what you've built not only works technically, but also actually helps users do what they are trying to do. Take a login feature, for example. Maybe your app lets users log in with their Google account or create a new account from scratch. In feature testing, you would test both of those passes, not just whether they work, but whether they make sense from a user's point of view. Do the buttons work? Are error messages helpful? Is the process smooth? Now, here is something important. A feature might be built by more than one developer. One person might handle the Google login, another might work on the new user flow. So it's essential that all the developers who touch that feature also test it together. It's not just about making sure your own part works, it's about ensuring everything fits together the way it should. So, in short, feature testing is all about verifying that features are reliable, usable, and user friendly, and that everyone on the team takes part in making that happen. All right, so now that we have tested all the individual parts of your system, like features and units, it's time for the big one, system testing. System testing is all about seeing how everything works together. You are not looking at one feature anymore, you are testing the whole application from the top, top to down. The first thing you want to check is, are the features interacting in weird or unexpected ways? Sometimes two perfectly working features clash when they used together, and that's where system testing really shines. Next, you want to see if the system supports what real users are trying to do. It's not enough that the buttons and forms work. They need to work together to support actual workflow, like first sign up, then browse, and then purchase. Then there is environment testing. Your app might work great on your machine, but what about on a slower network or an older phone or in Firefox instead of Chrome? System testing makes sure your app performs consistently across different platforms and settings. And finally, we test quality attributes. Is the system responsive? Can it handle multiple users at once? Is it secure and stable? All of this gives you a big picture view of your system's health and helps you spot problems you would miss if you only looked at features in isolation. If you want to test a system in a way that actually reflects how users are going to interact with it, scenario-based testing is the way to go. The idea is pretty simple. You start by defining scenarios, realistic situations where a user is trying to get something done. Maybe it's buying a product, submitting a job application, or booking a hotel room. From there, you identify the end-to-end pathway that user would take. This isn't just clicking a button, it's the full journey from logging in, navigation through options, entering data, all the way to completing the task. And here is the cool part. Every time you release a new version of your system, you run these same scenarios again. That way, you are constantly validating that the user experience still works as intended and you are catching bugs before your users do. It is a practical, user focused way to do something testing, and it's especially useful when your system evolves over time. Let's talk about release testing. That final check before your software goes out into the real world. Now, release testing is a little different from normal system testing. With system testing, you're trying to catch bugs and fix them. But in release testing, your focus shifts. You're asking, is this good enough to ship? It's done in the real environment where users will actually run the system, not some controlled test setup. Um, and that makes a big difference. You will start seeing messy user data, edge cases you didn't think of, and real world issues that your clean test cases didn't catch. Also, the bar is different. In earlier testing, if something fails, it's a red flag. But here, if a tiny bug shows up that only affects a tiny percentage of users and doesn't break anything major, you might decide it's okay to go ahead. The release testing phase also involves preparing the system for deployment, like bundling it into a container, installing libraries, setting up environments, and making sure everything runs smoothly once it's deployed. So the goal isn't perfection, it's readiness. Is the product stable, useful, and reliable enough that you feel confident putting it in users' hands? Let's talk about automated testing. Why it's a game changer for building reliable software. The idea is pretty simple. Instead of manually checking if something works, you write a script, an executable test that does it for you. Each test includes three things. First, some input data. This is what you give the function or method. Second, an expected result, what the correct output should be. And third, an assertion that checks whether the actual result matches the expected one. If they match, the test passes. If not, something off, and it's time to debug. Okay. And here is the thing, you don't just write one or two tests. Uh, okay, so let me just review if we miss something here. Yeah. For most real-world software, you will have hundreds or even thousands of those automated tests. That way, anytime you make a change, you can rerun all your tests instantly and see if anything broke. Um, okay, here, let's take a moment to see how automated tests actually run behind the scenes. So imagine you've written a bunch of test files. Each one of those files says, here is the input I will feed into the code. Here is what I expect back, and here is how I will check if it worked. Now, you don't run these tests one by one manually. Instead, we use something called a test runner. Think of it as a command center. The test runner takes each test file, runs it against your code, and uses a testing framework to handle all the behind the scene logic, like checking if your results match expectations. After all the tests are run, the test runner gives you a report. It tells you which test passed, which failed, and sometimes even why. This process is what makes automated testing so powerful. You can run hundreds of tests with a single click and instantly know if your code is solid or if something broke when you made a change. When you're writing automated testing, um, there is a simple and powerful pattern you should follow. Arrange, act, assert, often called the AAA pattern. So what does that look like? First, you arrange. This means you get everything ready. You define your test inputs, and if your code depends on something that's not built yet, like an external API, you use mock objects to stand in for it. Next comes act. This is where you actually call the function or the piece of code you're testing. It runs using the setup you created. And finally, assert. This is where the magic happens. You check if the outcome is what you expected. If it is, great. If not, your test fails and you've got something to debug. And here's a pro tip. If you're using equivalence partitions to pick your test inputs, which you should, don't just test the good cases. Include the weird edge cases and invalid inputs, basically anything that might cause your code to behave unexpectedly. That's how you make your test not just run, but actually protect your code. When users use a software product, they usually interact with it through the GUI. That's what they click, tap, or type into. But when it comes to testing, especially automating those tests, GUIs can actually make life a lot harder. That's because GUI-based tests are more fragile. A small version change can break your entire test suite, even if the functionality hasn't changed at all. So here's a smart design move. Expose all your core features through an API, not just the user interface. This way, when you write your feature tests, you can test everything directly through the API. No clicking buttons, no dragging windows. It's faster, more reliable, and way easier to automate. And there is another big benefit. If you ever want to redesign your user interface or build a new one for mobile, for example, you can do that without having to change your back-end logic. That's because your functionality lives in the API, not in the UI. This approach gives you software a longer life and it makes it much easier to maintain and evolve over time. So let's break this down. Imagine you're using a mobile app or website. That's the top layer here. When you click something or submit a form, you're really just sending a request to an API in the background. Now, what's powerful about this setup is that the API sits right in the middle. It acts like a translator between the interface you see and the core features that do all the heavy lifting. So why does this matter for testing? Because instead of building expensive, fragile tests that simulate button clicks, we can just test those same features through the API. It's faster, more reliable, and super scalable. Let's say we are testing the login feature or some payment logic. We can just call those through the API, check the results, and boom, we know it works regardless of what the GUI looks like. Even better, if we ever redesign our front end, like switching from a web app to mobile, or our tests don't break because the core logic is still as accessible the same way through the API. This is why modern development puts so much emphasis on API first design. It gives you the flexibility to build, test, and grow efficiently without being tied to how your interface looks. Let's talk about system testing. It's where things start to feel a lot more real. At this stage, we have already tested individual features, but now we want to see how everything works together. So we act like a user. We click around menus, fill out forms, hit buttons, basically walk through the software just like someone would in the real world. The goal here to catch any weird issues that pop up when different parts of the system interact. Maybe a certain order of clicks crashes the app, or a combination of inputs leads to a bug. This is where we would find that. Now, here is the catch. Doing all this manually over and over again can be super repetitive and honestly kind of exhausting. You're likely to miss something or just not click as fast the second time. That's why we use automation um, tools that record everything you do. Um, like a screen recorder, but smarter. It logs each click, each input, and lets you reply that exact sequence automatically. So when you make changes to your code, you can rerun the same test and instantly know if anything broke. It's a game changer for testing at a scale, and it's what makes modern QA so efficient. Let's take a look at how automated system testing can be streamlined using user interaction playback. Imagine you are testing a web or mobile app. You start by recording all your clicks, form entries, and menu selections, basically everything a user would do. This is handled by a user action recording tool. Now, instead of repeating those steps manually every time the system changes, the tool saves your session. These saved session or interaction records can be played back automatically. It's like hitting reply on a screen recording, but with real data flowing into your application. The cool part, all of these ties into your system's API. So the test doesn't just click buttons blindly. It's actually verifying if the system behaves correctly behind the scenes, just as it would be in the real world scenario. This method not only saves you time but also ensures consistency. You can run the same test again and again after each update and be confident your app still works the way it should. It's a powerful way to test how real users interact with your software without relying on real people every single time. Let's talk about a concept that flips the traditional way of writing software on its head, test-driven development or TDD. Instead of writing your code and then testing it, TDD asks you to do the reverse. First, you write a test, but not just any test, a test that will fail because the functionality hasn't been built yet. Then you write just enough code to make that test pass. This cycle, write a failing pass, write the code, make the test pass, is repeated over and over as you build your software piece by piece. TDD really shines when you're working on small, focused components like individual functions or classes. It's a great fit for unit testing. And now, while it sounds like a dream to clean, bug-resistant code, it's not perfect for everything. Once you start dealing with big systems or anything involving a GUI, like buttons, screens, or user input, TDD becomes a bit trickier to manage. Even the biggest fans of TDD will admit that automating tests for user interface isn't always straightforward. So TDD is a powerful tool, especially for back-end logic and clean design. But like all tools, it's best when used in the right context. All right, now let's walk through what the test-driven development workflow actually looks like in practice. It starts pretty simple. You have got a new feature in mind that you might need to build. Instead of jumping into code right away, you first break it down into something small that you can tackle. Then comes the key TDD moment. You write a test that's supposed to fail. This might sound weird, but it helps you clarify what your code is supposed to do. It's like setting a goal. After that, you run all your tests. Of course, this new one fails. That's expected. And now you write the minimal code necessary to make that test pass. Nothing extra, just what's needed. Once that's done, you run all the tests again. If they pass, you can breathe a bit easier, but don't stop there. You now refactor. That means cleaning up your code, making it neater or more efficient, but without changing its behavior. And then you loop back, pick the next chunk of functionality, write a failing test, and repeat. This tight loop ensures that your code is always backed by tests, which leads to more reliable, maintainable, and understandable software. It's a bit of a mindset shift, but once you get into the right rhythm of it, TDD can be a powerful way to develop software. Let's talk about security testing and why it matters more than ever. At this core, security testing is about protecting your system from attacks. The goal isn't just to detect bugs or crashes, it's to identify weak points that a real world attacker could exploit. We are testing to make sure the system can resist a variety of threats. Maybe someone's trying to overwhelm the system and take it offline. Maybe they are injecting harmful code. Or maybe they are trying to get their hands on user data or impersonate someone. To truly test a system security, though, you need more than just good intentions. You need real expertise. That means understanding how software can break, knowing where vulnerabilities usually hide, and using the right tools to simulate those attacks. Because at the end of the day, it's not enough to build a system that works. You have to build one that holds up under pressure. When we talk about risk-based security testing, we are talking about being strategic. Instead of testing everything blindly, we start by identifying what can go wrong, what kinds of attacks are likely, and which ones could do the most damage. Once we understand those risks, we design our tests around them. We might use automated tools to scan the system for things like open ports or outdated libraries. That's fast and helpful, but it's not enough. Some vulnerabilities are subtle. They require a human eye, someone to manually check how the system behaves under stress or how it handles unusual inputs. By focusing on the highest risk and combining automation with human judgment, we make our security testing smarter, faster, and more efficient. Let's talk about some of the most common security pitfalls we see in modern software systems. First up, unauthorized access. This can happen when an attacker gets their hands on someone's credentials or when an authorized user ends up accessing things they are really not supposed to. Sometimes the system just doesn't catch these unauthorized actions due to weak authentication. Next, we've got injection attacks like SQL injection. This is where someone sends in malicious database queries to pull or modify your data. Not fun. Add to that session hijacking, like when cookies aren't properly secured and someone else can pretend to be you. And then, of course, there is data exposure. Whether it's forgetting to encrypt sensitive information or leaking your encrypt keys. Either way, your data is wide open to anyone who wants it. The point here is these risks are avoidable, but only if we are actively testing and planning for them. When it comes to securing your system, identifying the risk is only half the battle. The real work begins when we try to understand how the risk could play out. Take, for instance, the case of an unauthorized attacker gaining access. Now, that might sound like a single threat, but it can happen in a bunch of different ways. Maybe a user picked a super weak password. Maybe the system's password file got leaked. Or maybe someone just fell for a phishing scam. All of those are real passes to the same bad outcome. Once we map out those possibilities, that's when we start designing focus tests. For example, we could write a test that ensures users can't set weak passwords or that two-factor authentication is enabled and enforced. The goal here isn't just to react to problems, it's to proactively test the system against the ways it can be attacked before anything goes wrong. Let's talk about one of the most underrated tools in software development, code reviews. A code review is when someone other than the original developer looks at the code and gives it a second pair of eyes. They are not just hunting for typos, they are checking for logic errors, poor design choices, potential security issues, or even just things that could be done more efficiently. And here is the important part. If something's off, it's the developer's job to make those changes. It's not about blame, it's about building better software together. Now, this isn't meant to replace testing. In fact, code reviews complement testing beautifully. They can catch bugs that would only show up under weird edge cases or highlight problems that come from misunderstanding how something's supposed to work. That's why a lot of companies won't even let code into the main product until it's been reviewed. It's about ensuring quality, consistency, and shared understanding across the team. In short, code reviews help you write cleaner, safer code, and they make you a better developer too. When you're reviewing Python code, these are some really important things to keep an eye on. First up, naming. Are the variables and functions clearly named? If I see a variable called, for example, x1, I have to include what it's doing, but total price or user email, much better. Next, what happens when things go wrong? It's easy to write tests for cases that work, but did the developer write tests for bad inputs like empty lists, invalid types, or missing data? And then exception handling is another big one. If something unexpected happens, does the program crash or does it handle it gracefully? For Python especially, default parameters are powerful but can be misused. So you want to make sure they are used intentionally. Then there is type consistency. Python won't stop you from reassigning a variable from a string to a list to an int, but that doesn't mean you should. Consistency helps with debugging and readability. And finally, indentation. This is huge in Python. Forget a tab or add one in the wrong place, and suddenly your if condition is doing something you didn't intend. All of these little things, when done right and up to clean, reliable code. Okay, thank you for watching this video and have a great time.